All right, so one more example of that, this process with a definite integral. So I'm going to do the integral from 0 to 1 of inverse tangent of x. So it's not obviously an integration by parts, except that you don't have any way to get the antiderivative of inverse tangent. But you do know the derivative of inverse tangent. That's one you should absolutely know as 1 over 1 plus x squared. So what we're going to do is we're going to use the inverse tangent of x as the u, and we're going to have dv be 1. The 1 right here that we don't see. That's going to be our dv. All right, so then we're going to say u equals inverse tangent x, du equals 1 over 1 plus x squared dx. That's what you should really know. We're going to use that a lot later this year. And then we have dv and v. And our dv is just 1 dx, or let's just say dx. And then our v is the antiderivative of 1 is just x. All right, so then we're ready to write our integral as uv minus the integral of v du. So for our uv, we're going to write inverse tangent x times x. I like to put the x first. I think that's a little clearer. So we're going to write x inverse tangent x. But since this is a definite integral, my uv part, I have to put an evaluation bracket on it. We're doing 0 to 1 there. And then I have minus, so then it's going to be the integral of my v du is going to be x times 1 over 1 plus x squared. And of course I could put the x on the top, you could put the dx on the top, you're welcome to do those things. So now, and this is 0 to 1, right? Because it's a definite integral, so it takes the same limits. So watch, where the limits are and make sure everything's complete and correct as you go. All right, so now when I go to do this one, what am I going to use? Am I going to use parts again? I'm going to do the derivative of this one. I don't want an antiderivative of that one. Do I want an antiderivative of this one? Do I want a derivative of this one, an antiderivative of this one? I mean, you could think about that. But here's an easier thing to do. Use a substitution where this is u and this is du. So again, we're mixing our methods, so we're going to use substitution. So we're going to use a substitution with u equals 1 plus x squared. And you just really have to develop some experience with these to see when it's going to be beneficial to use which. I see in a denominator, I see a function, and then I have the derivative of that in the numerator. That's telling me that I should use substitution with u equals the denominator. So then I have 1/2 du. And these are the things you should write to support your work. So now when I go down to the next line and I start doing my substitution down here, right? What I'm not going to do is leave this off. All right, I'm going to keep that in there. So I could evaluate it right away. You could do that if you want to. But what I'm not going to do is just drop it and then put it on at the end. All right, now I'm also doing here, my integral is 0, 1. That's my quirky thing that I do where I don't change the limits of integration, and then I just substitute the function back at the end. If you like, you can use your u and change the limits of integration. What would they be? I would do u of 0 is 1, so I do 1, and then u of 1 is 2. So I do the integral from 1 to 2, and then I don't have to substitute back in at the end. All right, so that's an option you have open to you that some people would like better. All right, so, but I don't, so whatever. X dx we're replacing with 1/2 du, so let's put the 1/2 out here, and then the du is going to be our du, and then I'm going to substitute, so my x dx already took care of this x right here, so now I just have 1 over 1 plus x squared, but the 1 plus x squared is u, so I have 1 over u du. So typically, when you see this, a function in the denominator with its derivative in the numerator, that's going to be a u substitution that's going to give you a 1 over u, that's going to give you an ln. That's also going to become a big useful deal later on. So just that whole process. All right, so now I have minus 1/2 ln of absolute value of u from 0 to 1. Of course, if you change the limits, you could just plug them in right away. I didn't, so I have to plug the original function back. I keep writing this over and over again. You could evaluate it and then write what you evaluated over and over again, but you cannot just drop it off. Otherwise, your lines are incomplete. So now this is ln of absolute value of 1 plus x squared. I'm keeping the absolute value. You could do something like at this point, say, oh, I know that 1 plus x squared is always positive, therefore I could drop the absolute value. You could do that. Or you could wait till you plug in the 1 and plug in the 0 and then realize you don't need the absolute value, which is what I'm ready to do, which is plug in values. So now I'm going to plug in the 1. So I have 1 times, what's the inverse tangent of 1? Huh? What's the inverse tangent of 1? You got your unit circle memorized? It's pi over 4. All right. And then I have 0 times, just check to make sure this is not undefined. It's not. Inverse tangent of 0 is 0. So I just have 0 times 0. I'll go ahead and write that. It's not going to kill me to write it. That's my first one. I'll put it in parentheses just for fun. And then minus 1/2 times. All right, so what's this going to be? I'm going to plug in the 1, and I'm going to get ln of 2. I'm going to plug in the 0, and I'm going to get ln of 1. You could say that that's 0 right away if you want. You could put this in your calculator and get a decimal, but why? Why would you put it in your calculator and get a decimal? When it's pi over 4 minus 1/2 ln 2, we all know ln of 1 is 0, so this is your answer. Isn't that a nice answer than some big jumble of decimals? All right, it's very nice. There you go. Now, what is your homework on this, I hear you saying through TV land? Well, it's that. We're going to do Rogowski, page 403, 404, posted, 7 through 13 odd, 19 through 27 odd, 49, 50, 51. That should keep you busy for a while.